Now we're going to go ahead and look at some important exceptions to the octet rule. So these rules we've been using for drawing these Lewis structures. So sometimes ions or molecules, they can actually have an odd number of electrons. And so since electrons are paired up in bonds and paired up in lone pairs, these odd molecules, they're what are called radicals. Um, and they're fairly rare in this case, but they can be both molecular or ionic. And some examples of this are the chlorine dioxide, nitrogen monoxide, nitrogen dioxide. So these are some three examples. If you calculate the total number of valence electrons for each of these species, you'll find that you'll come up with an odd number of valence electrons. And so this is what the particular Lewis structures would look like. What you do end up doing is just sticking one of those lone electrons, not a pair, but lone electrons on one of the two atoms, and the atom that gets a single electron. So the better Lewis structure here would be the one where the formal charge is actually minimized again. If you look over here, this one has a formal charge of 0 on both atoms. Over here we would have a formal charge of +1 and -1, if I'm not mistaken. No, this one would be +1, this one would be -1. And so if you look at, go ahead and actually pause the video and see if you can calculate that and find that this one would be +1, this one would be, no, this one would be +1, this one would be -1. Make sure you can actually calculate those. So some ions or molecules have less than an octet, and oftentimes a good giveaway for this is a lot of atoms that have boron as their central atom. A lot of molecules that have boron as their central atom will have this what's called a limited octet, or an octet, a number of electrons around it that's less than an octet. So if when you're filling the octet of a central atom, it results in a negative charge on that central atom and a positive charge on one of the outer atoms, when you're calculating formal charges, don't fill the octet of the central atom. Just fill the octet of those outer atoms and leave the octet of the central atom unfilled. So here are some examples of that. These are all boron trifluoride. So boron trifluoride, you see that this is a Lewis structure here, but it does not have an octet for boron in the center. However, all of the formal charges on all the atoms is 0. If you try to write it any other way, any of these other possible resonance structures, what you'll find is that you'll have a -1 charge on the central atom and a +1 charge on the fluorine atoms. So these are not good. This is the best, or this is the correct Lewis structure there. So this is the most important, and these are less important. Finally, sometimes you'll actually have a central atom with what's called an expanded octet. Now this can only occur with an atom who's in row 3 or below. Now if you think about it, the reason why it has to be in 3 or below is that expanded octet, those electrons, it's got to have essentially an empty D shell, or a possible D shell that doesn't have electrons in it. This is what's called hypervalence. So extra valence, remember valence electrons, if you see hypervalent, think extra electrons. And here's an example of what happens when you have this expanded octet. And this occurs when, if you have filled out the octets for all of the surrounding atoms and filled the octet for the central atom, you still have atoms left over, or electrons left over. You stick those electrons on the central atom.